Welcome back to the deep dive. If you're following along with our chemistry journey, maybe you just geek through thermodynamics, figuring out if a reaction can even happen.
Right, the spontaneity question.
Exactly. So today's deep dive tackles the very next logical question. Okay, it can happen,
Mm.
but how fast?
Uh-huh. And that's absolutely critical in the real world, isn't it? Knowing a reaction is possible on paper doesn't help much if it takes like a million years.
Or if you need 20 million tons of ammonia per year, you can't
Yeah.
just wait for nitrogen and hydrogen to maybe react eventually.
Precisely. You need to understand the speed, the rate, and ideally control it.
And that's exactly what our source material digs into today. It's all about chemical kinetics.
Yeah, kinetics, the study of reaction rates, basically how fast reactions go and what affects that speed. It's the dynamic part, moving from if to when.
So the sources start, logically enough, with the idea of the reaction rate itself,
Mhm. And it's important to distinguish, right? We might casually say a reaction is fast or slow.
like striking a match super fast,
Mhm.
or iron rusting very slow.
Exactly. That's qualitative. Kinetics demands something more precise, a quantitative measure.
A specific number. So reaction rate isn't just speed, it's a value telling you how much the concentration of something, a reactant or a product, changes over a certain time.
Right. And typically in, say, a first-year chem context, you're looking at concentration in molarity, that's moles per liter, capital M,
Okay.
and time, well, often it's in seconds. So the rate units frequently end up being molarity per second, M over
You got
S.
it, m per second. And the basic formula, the sources say, is just the change in concentration divided by the change in time. Delta concentration over delta time.
That's the core idea. Rate equals delta concentration over delta time. Now, there's a small convention to remember.
Okay.
Well, reactants get used up, right? Their
Yeah.
concentration goes down over time.
Sure.
So the change in reactant concentration is negative. To make the reaction rate itself a positive number, which is usually more convenient, we just stick a negative sign in front of the rate calculation for reactants.
Ah, okay. So rate of consumption of A is minus delta A over delta T.
Exactly. And for products, their concentration goes up, so the change is already positive. The rate of formation of B is just delta B over delta T, no extra negative sign needed.
Makes sense. Keep the rate positive.
Now, stoichiometry, the numbers in the balanced equation becomes really important here.
How so?
Well, let's take a super simple reaction. A just turns into B, 1-to-1, A, B.
All right.
In that case, for every molecule of A that disappears, one molecule of B appears. The rate of disappearance of A is exactly the same as the rate of appearance of B.
Okay, same rate. If A drops by, say, 10 m in 10 seconds, B goes up by 10 m in 10 seconds.
Precisely. And the rate for both, using our formula, would be 1 m per second.
But what if it's not 1-to-1? Like the source mentions A to B.
Good example. Now think about it. For every one molecule of A that reacts,
You get 2 molecules of B.
exactly. So if A's concentration drops by 10 m in 10 seconds, its rate of disappearance is still 1 m per second.
Then B's concentration must go up by 20 m in that same time.
You got it. So B's rate of formation is 2 m per second, twice as fast as A is disappearing.
Huh. So the rate depends on which chemical you're actually measuring. That seems messy.
It would be, yeah. Which is why we define a single standardized reaction rate that accounts for this.
How does that work?
You take the rate of change for each substance, remember, negative for reactants, positive for products, and you divide it by its stoichiometric coefficient from the balanced equation.
Ah, okay. So for a general reaction like AA plus BBCC plus DD,
The standardized rate would be minus 1 over A times delta A over delta T,
which equals minus 1 over B times delta B over delta T,
which equals plus 1 over C times delta C over delta T.
and plus 1 over D times delta D over delta T. They all become equal.
Exactly. That gives one consistent rate for the overall reaction no matter what you measure.
The sources use that N2O5 decomposition example, right? 2N2O5 gas goes to 4NO2 gas plus O2 gas.
Yeah. And if you look at the data they provide for, say, between 200 and 300 seconds, you'll see the rate that NO2 appears is double the rate N2O5 disappears.
Because the coefficient for NO2 is 4, and for N2O5 it's 2. 4 is double 2.
Right. And the rate O2 appears is half the rate N2O5 disappears. Coefficient of 1 versus 2.
So dividing by the coefficients 2 for N2O5, 4 for NO2, 1 for O2, makes all those different measured rates give the same overall reaction rate number.
That's the idea, standardization.
Okay. And another key thing the sources mention is that rates usually aren't constant, are they? They tend to slow down.
Generally, yes, because as the reaction proceeds, what happens to the reactants?
They get used up, their concentrations decrease.
And if there's less stuff around to react, it makes sense that the reaction would slow down, right? Fewer collisions, fewer chances for reaction.
Right. So the rate changes over time. This leads to the difference between average rate and instantaneous rate.
Exactly. Average rate is like your average speed on a whole road trip, total distance over total time. You calculate it over a finite time interval. Instantaneous rate is like looking at your speedometer right now. It's the rate at one specific moment in time. Mathematically, it's the slope of the line tangent to the concentration versus time curve at that point.
And you mentioned the initial rate is particularly useful. That's an instantaneous rate at time 0.
Pretty much, yeah. Measured right at the very beginning, before concentrations have changed much. It's often easier to measure and really important for figuring out how rate depends on concentration.
Which sounds like a perfect lead-in to the rate law.
It is indeed. So we know how to measure a rate, but how do we predict it or relate it mathematically to the concentrations? That's the rate law.
Okay. And the sources give a general form, like rate K times A to the M times B to the N for a reaction with reactants A and B.
That's the typical form, yes. Usually describing the rate early on when any reverse reaction is negligible.
Let's break that down. A and B are the concentrations of the reactant.
In molarity, usually.
K is the rate constant. What's that?
K is a proportionality constant. It's specific to a particular reaction at a specific temperature. It sort of bundles up everything else that affects the rate, besides concentration, like temperature and the inherent reactivity.
Okay. And then M and N. Those are the reaction orders.
Yes, M is the order with respect to reactant A. N is the order with respect to B. And the sum, M plus N, is the overall reaction order.
Now, the sources make a huge point about M and N, right? They are not the stoichiometric coefficients A and B from the balanced equation.
Absolutely. Critical point. Cannot stress that enough. You cannot generally look at the balanced equation AA plus BB A products and say the rate law is KA BAB.
Yeah.
It just doesn't work that way most of the time.
So where do M and N come from?
Experiments. They must be determined experimentally. Always.
Okay. And what do these orders actually mean, like physically?
They tell you how sensitive the reaction rate is to the concentration of each reactant. If M is 0, 0 order.
Rate, Ka0K. The rate doesn't depend on A's concentration at all.
Correct. If M is 1, first order, rate equals Ka1. Double the concentration of A, you double the rate. It's directly proportional.
Makes sense.
If M is 2, second order, rate equals Ka2. Now, if you double the concentration of A...
2 squared is 4. You quadruple the rate.
Exactly. So the order tells you the concentration dependency.
And the units of K, the rate constant, they have to adjust based on the order, don't they?
You got it. The units of K are a good clue to the overall order.
So how do we do these experiments to find M and N? The sources mention the method of initial rates.
Yes, that's a very common way. The core idea is clever. You run the reaction several times.
Oh.
In each run, you change the initial concentration of just one reactant, keeping the others constant, and you measure the initial rate for each run.
Ah, so you isolate the effect of each reactant.
Precisely. If you run it once, then run it again doubling only A, and you observe the initial rate also doubles.
Then the rate is proportional to A to the power of 1. It's first order in A, so M1.
Exactly. If doubling A quadrupled the initial rate.
That's the 22 relationship, second order in A, M2.
And if doubling A had no effect on the initial rate?
That's the weird one. 0 order in A, M0.
Right. You repeat this process, changing B while keeping A constant to find N.
The N205 example data in the sources showed this, didn't it? They had runs where they doubled the initial N205.
Yes. And the initial rate also doubled from 4.8 by 10 to 6 m's to 9.6 by 10 to 6 m's, when N205 went from 1.0 by 10 to m to 2.0 by 10 to 2m.
Doubling concentration, double the rate.
Yeah.
Clear first-order dependence. Okay, so rate law connects rate to concentration at a given moment. But what if I want to know the concentration after some time has passed, or how long it takes to reach a certain concentration?
Now you're asking for the integrated rate law, also sometimes called the concentration time equation.
Integrated implies calculus.
Yep, it's derived by integrating the rate law equation. But you don't necessarily use calculus to use the result.
Okay, good. And its purpose is?
Its purpose is exactly what you asked. It relates concentration directly to time. If you know the rate constant K and the initial concentration A0, it lets you calculate the concentration at any time T, or flip it around, calculate the time T needed to reach a specific concentration.
And like the rate law itself, the form of this integrated rate law depends on the reaction order.
It does. They look different for 0, first, and second order reactions. The source highlights the first order one, ln of concentration at time t equals minus k times t plus ln of the initial concentration. Notice it's in the form y equals mx plus b. So if you have concentration data over time and you plot the natural log of the concentration versus time and you get a straight line,
Then you know it's a first-order reaction, and the slope tells you the rate constant k. That's neat.
it's a very common graphical method to determine order and k. For second order, by the way, plotting 1a versus time gives a straight line with slope ek.
Handy. And the source had an example calculation using the first-order integrated rate law.
Yeah, something like a goes to p, first order, k equals 4.00 by 10.3 s mass 1. How long does it take for A to drop from 0.750 m down to mass 0.180 m? Do the math with the natural logs.
And it came out to about 503 seconds, or just over 8 minutes.
Right. A direct prediction of time based on the kinetic.
The sources also mention half-life T1 half.
T12. That's simply the time it takes for the reactant concentration to drop to exactly half of its initial value.
Useful concept.
Very useful, especially for first-order reactions, because their half-life is constant. It doesn't depend on how much you started with. It takes the same amount of time to go from 100 to 50 as it does to go from 50 to 25.
Interesting property. Okay, so we've got rate, how concentration affects it, rate law, how concentration changes over time, integrated rate law. But we're still talking kind of macro level. What's actually happening with the molecules? The step-by-step.
Now we're moving into the realm of reaction mechanisms.
Okay.
As the sources explain, most reactions you see written as a single balanced equation don't actually happen in one big smash-up of all the reactant molecules.
Seems unlikely for complex reactions, yeah.
Instead, they usually proceed through a sequence of simpler, more fundamental steps. These individual steps are called elementary steps.
Elementary steps.
And the whole sequence of these elementary steps, that's the reaction mechanism. It's the detailed pathway from reactants to products.
What's special about an elementary step?
The key thing is that an elementary step represents an actual molecular event, like one molecule breaking apart, unimolecular, or two molecules colliding, bimolecular. Because it's fundamental, its rate law can be written directly from its stoichiometry, or more accurately, its molecularity.
Ah. Unlike the overall reaction, so if an elementary step is A plus BP, its rate law is KAB.
Yes, if it's truly an elementary step.
And mechanisms often involve intermediates.
Right. Intermediates are species that get formed in one elementary step and then consumed in a later step. They are temporary players. They don't show up in the overall balanced equation because they are produced and then used up within the mechanism.
Okay. So a sequence of steps, maybe involving intermediates.
Yeah.
How does this relate back to the overall rate we measure?
Well, in most mechanisms, the elementary steps don't all happen at the same speed. There's usually one step that is significantly slower than all the others.
The bottleneck.
Exactly. That's called the rate determining step, or RDS. It controls the overall speed of the reaction, just like the slowest car in a single lane of traffic determines the flow rate.
So the overall reaction can't go any faster than its slowest step.
Correct. And here's the crucial link. For a proposed mechanism to be considered plausible, the rate law derived from its rate determining step must match the rate law that was determined experimentally for the overall reaction.
Okay, that makes sense. The theory has to match the observation. The sources used NO2 plus CO, goes to NO plus CO2 as an example.
Yeah, good one. Experimentally, chemists found the rate law for that reaction is rate equals KNO22. Notice, CO concentration doesn't even appear in the rate law.
Huh. So a simple collision between NO2 and CO can't be the whole story, or CO would be in the rate law.
Right. So a plausible mechanism proposed is a two-step process. And NO3 is the intermediate. Now, what's the rate law for the slow step, step 1?
It's an elementary step by molecular collision of two NO2s. So its rate law should be rate equals KNO2NO2, which is KNO22.
And what was the experimental rate law?
Also, rate equals KNO2T2. They match.
Bingo. That match strongly supports this two-step mechanism as being plausible. It explains why the rate depends on NO2 squared and not on CO.
Very cool. It unpacks what's really going on.
There's another quick example in the sources, NO2 plus F2 arrow AO NO2F. Experimental rate is KNO2F2. The proposed slow step is NO2 plus F2 NO2F plus F, a fluorine atom intermediate, which directly gives that rate law, again, plausible mechanism.
So mechanisms give us the how, but digging even deeper, why do reactions happen when molecules collide? What makes a collision actually work?
Back to fundamentals. That's collision theory. It's a model that explains the basic requirements for a collision to be effective, meaning it actually leads to products.
And the sources list two main requirements.
That's right. Two key things must happen. First, energy. The colliding molecules have to smash together with enough energy.
Enough to do what?
Enough to overcome an energy barrier called the activation energy, often symbolized Ia. Think of it as the minimum energy needed to get the reaction started, maybe to break some existing bonds first.
Right. Like pushing a ball over a hill before it can roll down the other side. You need that initial push, the activation energy.
Perfect analogy. So sufficient energy is requirement number one. Requirement number two is orientation.
Orientation, like how they hit each other.
Exactly. The molecules have to collide in the right way, lined up correctly, so that the specific atoms that need to form new bonds can come into contact, and the bonds that need to break are strained.
Like puzzle pieces, they only fit if they're oriented correctly.
Precisely. A collision could have tons of energy, but if the molecules hit bumper to bumper when they needed to hit side-on, nothing might happen.
So energy and orientation are needed for an effective collision.
Correct. And the more frequent these effective collisions are, the faster the reaction rate.
This must be where the Arrhenius equation fits in.
That equation beautifully connects the rate constant K to the activation energy, EA, and the absolute temperature, T. R is the gas constant.
Day.
A is the frequency factor. It's related to both the total frequency of collisions and the probability that a collision will have the correct orientation.
So higher temperature T makes the exponential term less negative, closer to 1, increasing K. Lower activation energy, EA, also makes the exponent less negative, increasing K. That makes intuitive sense.
It does. Higher temp means more molecules have enough energy to overcome EA, and they collide more often. Lower EA means it's an easier hill to get over. Both speed things up.
So let's quickly recap the factors affecting rate, tying it all together. Concentration.
Higher concentration means more molecules packed together, leading to more frequent collisions, reflected directly in the rate law. Higher temperature means molecules move faster. More frequent collisions, and more importantly, a higher fraction of those collisions have energy greater than Ia. Big impact on K via Arrhenius.
Surface area. The sources mention this for heterogeneous reactions.
Right. If you have a solid reacting with a liquid or gas, increasing the solid surface area provides more sites for collisions to occur, like grinding up a solid.
And finally, catalysts. The sources list them but didn't go deep into how they work in this section.
Right. Catalysts are substances that speed up a reaction without being consumed themselves. Very often, they work by providing an alternative reaction pathway, a different mechanism that has a lower activation energy.
Ah, so they lower the hill, making it easier for collisions to be effective, even at the same temperature.
That's a common mode of action, yes.
Wow, okay. So we've gone from just asking how fast to defining rate, linking it mathematically to concentration with the rate law, tracking concentration over time with the integrated rate law, peering into the step-by-step dance of the reaction mechanism, and finally, understanding the fundamental collision requirements, energy, and orientation.
It's quite a journey from the macroscopic observation of speed down to the molecular level events. And understanding all this kinetic stuff is incredibly powerful for chemists.
Because it lets you predict and control things.
Exactly. It's not just about knowing if something reacts, but understanding the how and when, so you can tweak conditions, temperature, concentration, maybe find the right catalyst to make processes faster, more efficient, or even selectively produce the desired product.
It really shifts chemistry from just observing to actively manipulating. Which brings up a final thought, maybe it's something for you listening to chew on. If we can figure out these detailed reaction mechanisms, these precise sequences of molecular steps, how might that deep understanding allow chemists not just to improve reactions we already know, but maybe to actually design completely new reaction pathways, perhaps create molecules or materials in ways nature never figured out, maybe leading to more sustainable or efficient chemical processes.
That's the dream, isn't it? Rational design based on fundamental understanding. A really exciting frontier.
Definitely something to think about.